If several forces act, then the sum of their individual works is called the total work. Sort of duh. Your textbook points out that this could as well be called the net work, but this is deprecated because it's easily confused with the word network. So just an English glitch there. And this gives us a really important final result here, which is that if the total work is positive, then energy is transferred into the system, whereas if the total work is negative, then energy is transferred out of the system. So this is always the work done on a system, and when it's positive, we're doing work, and when it's negative, we're getting work. That's sort of an old school way of saying it, which we've moved away from. Sometimes they'll say, in the distant dim past, in the before times, people would say the system work is done on the system or work is done by the system. We're going to try and avoid that. So the APs have settled on saying work is done on a system, and then the sign of the work tells you what happens to the energy in that system. Right? Doing positive work on a system stores energy in the system, and doing negative work on a system takes energy out. Couple of things. If the object undergoes no displacement while the force acts, then no work is done. This is a little counterintuitive. Right? You might imagine a different way of looking at this is that if I said that your homework tonight was to grab your Chromebook and hold it straight out from your chest on your arm, extended as far as you can, and then just hold it for the next 8 hours, you'd probably find that kind of tedious and even onerous. And you'd say, I'm definitely doing work. And yet this definition says, but the Chromebook doesn't move, so you're not doing any work. What's the contradiction? Well, you're not doing any bulk work on the Chromebook, but the way that your muscles work, they are constantly flexing, in which you can't hold your arm straight out and it doesn't lock. It's always your muscles that are going on, and half of them are contracting and half of them are expanding, but they're moving, so their displacement allows work to be done. If you put your textbook on a desk and say, hey desk, your homework is to hold this textbook for the next 8 hours, the desk will not complain. Largely because you're not in a Disney movie and objects aren't animated and sing to you, but also because when you put it on the table, it settles in and then stops moving. And the table isn't continually flexing to hold it up, it just has adjusted its shape, and so no work is done. There are animals, I think largely herbivores, which lock their knees when they sleep, so they can sleep standing up and not lose any work, because they've basically put their legs into a locked position and they don't change as they stand. All right, force perpendicular to displacement doesn't do any work. We've already talked about this with some extent, so we're not going to go over it again. If the part of the object on which the force acts undergoes no displacement, no work is done. All right, even though wall pushes on skater with normal force N and Shin goes displacement D, the wall does no work because her point doesn't change. What does do work in this case? Her arms, the muscles in her arms and the leverage she puts around her elbow pushes her body away, but the wall is not pushing her away because it does not. The force it's applying is on a point that undergoes no displacement. All right, let's think about this one. A string is used to move a 1.2 kilogram puck in a circle of radius 2 meters at a constant speed of 2.3 meters per second along a frictionless table. How much work in joules is done by the tension in the string during one complete revolution? As always in physics, let's draw a picture. And we have our object, which is going to move with some velocity, but there's a tension pulling up this way. And all of that ends up being sort of redundant, because now that we look at it, the displacement is going to be in the direction of the velocity at any given instant, and that is clearly perpendicular, and perpendicular forces do no work, so 0 joules of work are done.